All right, we are live. I am going to be talking today about segment trees, and let's see how it goes. Let me start by sharing my screen. How do I do that? How do I do that? How do I do this? Okay. So yes, I guess we can see the screen. Can we see the editor? Now we can see the editor as well. Okay, so I've made some notes, but mostly it's going to be about segment trees, and we're going to start from the beginning because I made a previous attempt that did not work out so well. But hey, let's see. And I have this nice book here called algorithmica.org. But let's see if this is cool. I'm also going to rely on CPA algorithms, which is the classic website, right? So just going to be going through this. So okay, what are segment trees? So segment trees are effectively good for range queries, right? So if you have like a query which wants to perform like a range or update or a specific range of elements, so you want to find like a let's say, okay, you're given an array ARR equals to, I don't know, 10 minus 5 4 3 6 8, and you want to find, so the task is to find minimum element over a range. So the range could be, let's say, minimum from index 3 going up to index 5. So this would be min array 3 colon 5. And let's say the 5 is not inclusive. This is important. So basically what we are saying is consider ARR 3 colon 5, and this would be 0, 1, 2, 3, 4. So these are the indexes. So let's say these are our indexes, right? So 0, 1, 2, 3, 4. So what we are saying is we start with 3 and then take 4. So this will be element 6, comma 8, and then we want to find minimum over this. And this would be, of course, 6. So the answer would be 6, and then we are done. The catch is, so this kind of things can typically be answered directly using prefix sums. So the first guess should be prefix sums, right? Actually, not for minimum. The prefix sum will probably not be useful for minimum, or will it be? So this is a good question. Let me figure out question. Can we even use prefix array to build like a prefix min? Probably not. But okay, so if it was sum, let's say sum instead of min, it was sum. So let's do sum, and then the answer would be 8 plus 6 is yeah, so 6 to 14, right? And then now you're done. So this question can definitely with the answer using prefix sum array, because you can create like a pre which would start with like 10 and then have like 5 plus 3 8 plus 6 is 14, and then 14 plus 8 is 22. And now you can say, hey, sum of 3 colon 5 is actually nothing but pre 5 minus pre 3 minus 1, which is equals to pre 5 minus pre 2, and this would be pre 5 would be 0 1 2 3 4. So okay, actually, yeah, if we are inclusive here, so we're going to do, so this is inclusive. So yeah, pre 4 minus pre 2, and this would be 22 minus 0 1 2 8. And again, the result would be 14, because 22 minus 2 is 20, and then 20 minus 6 is 14. Okay, so we are done. So we're still getting the same answer, but this answer we get, it's going to be just much faster. So we're going to, so this will typically this would be like worst case naive solution. Worst case would be order n squared. actually just order n per operation, right? This would be constant time per constant time, because we are only like two index of array index operations plus one subtraction operation. So then it's basically free, right? Now, order n is not typically bad, and so why do we want to do better, and why do we want to construct this prefix sum array? Because you are not asked to just implement prefix sum. Like, you're not just asked to get like a sum for a single range. You're given a set of queries, right? So you're given a set of queries. So let's say the query, it's like, and this is going to be like a pair of tuple, right? So in this case, one would be 3 comma 4, so you'll have like 3 4. So let's say the queries in this case are of the format colon LR, right? With format LR. So let's say you're given 3 comma 4, and then you're given another which is like 1 comma 5, and then another which is like, I don't know, 2 comma 4, 0 comma 3, etc. So if each one of these operations is order n, so you're doing order n if you want to calculate some here, and then you're doing order n here, and then you're doing order n here, and then order n here. So you're doing 4 times order n, and so effectively, and the set of queries is a queue. So let's say the queue is kind of the size of this. Size is equal to q, and so your final solution would become final complexity would be order q times n, and that's bad. And in the most pathological case, you have, let's say you're just doing this, right? So 0 n minus 1, and then you're getting given another 0 and another n minus 1, and so on. And so now you're effectively saying, hey, you're doing your, so basically, and then let's say q is comparable to n. So now your q times n becomes approximately n squared. The other restriction which prefix sum is, what if the array was modified between the two query operations? So the prefix sum gets computed immediately the first time around, right? So the first time you get prefix sum, you're just given, hey, give me the prefix sum for this, and you get it. That's fine. But what if like the original array here was this? Like, this was the original array. So you calculate. So let's say you're given, hey, give me the sum of array 3 to 4, right? Or let's say, yeah, this was the sum that was given to you. Sum of this, but then someone comes in and says array of 0 becomes 20 instead of 10, and now you want to calculate a sum again from 0 to 4. I don't know, right? Let's say this was also 0 to 4. Now this becomes a problem. Why does this become a problem? It's a problem because your prefix sum was now just effectively useless. The prefix sum is still operating on older version of the array. You will have to recompute. This is not a great idea. I mean, it is a great idea. This will be slow. So now you have the same problem again, that if you let's say you decided to recompute prefix sum after every modification. So if you have like order n time for a ranged sum query, and order and let's say you have like one modification after every query, so you get order n time for recomputing the prefix sum array. So now you're effectively back to the start, right? So you're effectively doing quadratic time, which is not great. Actually, it's probably going to be worse than quadratic time. Let me guess. So if you're doing order n, and then you need to calculate, even after calculating, you need to do like a, yeah, order n recomputation plus order n to fetch the new. Yeah, okay. Yeah. Order 1 plus order and recomputation, and then order 1 plus order and recomputation, etc. So it'll still be bad, right? So nearly quadratic. So this is why prefix sums are not a good candidate when array is getting modified. Hope that's clear. Let's go to segment trees. So what are segment trees all about? So fundamentals of segment trees, it's going to store information about array intervals. So what are typically called sub segments. So the problem has to involve a range of consecutive elements. We know that. So right, so if you have an array 1, 2, 3, 4, 5, where array L to R, where L and R are indices of the array, that's fine. And these are the characteristics, right? So we need to find sum of all elements from L to R, and this is kind of a query operation. And then suddenly there's a quick modification like we just saw. And then again, or you need to find like another minimum. So sum is just one example of a query. You can also do like minimum, etc. Yeah, so do a query, do a modification, do another query, do a modification, etc., and do a modification on a subsegment. So these are the cases where segment trees are useful because what do segment trees allow you to do? They allow you to do all of these operations. So let's say the query operation as well as modification operation in log n time. That's the fundamental beauty of segment trees, where in a regular array, you would be you are either allowed to, like, if you're using prefix sums, you can do the query operation very fast, but the modification makes it slow, because after modification you need to do a recomputation, or the query itself is slow, but the modification is fast, right? So if you were just naively using an array and you wanted to query to find the sum, so then you need to iterate over all elements of the array, which is slow. But but then you can do the modification fast, because all you need to do is just index to the array and then change the element. So so with a naive array or with prefix sums, you can either have fast queries or you can have fast modifications. You cannot have both. Let me just write this down. Arrays or prefix sums, you can either have fast queries plus slow modifications. So this would be prefix sums, or you can have fast modifications plus slow queries, naive array solution. You cannot have both, and this is where segment trees shine. That's the idea. Okay, what else should we talk about? So something about advanced segment trees. We'll get to that once we understand what basic segment trees are all about. They can be the one nice thing about segment trees is they can be generalized to larger dimensions. So if you know how to compute like minimum queries for a single dimension array, you can also apply the same for a matrix, which is a 2 by 2 two-dimensional array, and then you can just compute them in log square n time. Segment trees do take larger amount of memory. That's fine. Kind of should be fairly obvious, but let's just get that out of the way. So, and something I'm just going to remember it. So the array, so the memory requirement for a segment tree would be 4n, right? So standard segment tree requires 4n. And where does this number 4n come from? It's just an upper bound over the number of elements that the array can have, that the tree can have, right? So let's just figure it out. So if we have like a and it's effectively like a binary search tree, where you're just using you're just doing divide and conquer. So you have like an array, you cut it into half, so this will become your root, right? The root has the sum of the entire array. You cut this root into half. Actually, let's just look at the picture here, right? Yeah. So this is a nice visual representation of segment trees. So we have an array starting from 0 going until 4, and we're storing the sum equals to 3. What we do is we cut it in half. So we store the first half here as a left child, and we store the right half as the second half as the right child. And then here we're also storing the partial sum, right? So sum equals 2, sum equals 1. These are the partial sums over this array. And then we recursively do the same. And that is the construction of this is effectively the visual representation of your segment tree. This makes sense. Now, what is this idea? Like, how can we calculate and estimate the space, and the equation is given here, right? So the number of vertices in the worst case can be estimated by the sum, and this is the equation of calculating the sum, which is you have one element, one vertex here, two vertices here, four vertices here, etc., etc. So if it's a complete segment tree, of course in this example it's not a complete one, because these three nodes, these three are leaf elements, they don't have further children. But if it was complete, it would be like that would be the worst case, and then you can just sum all of them up, right? So 1 plus 2 plus 4 plus up to going up to 2 raised to the power log n, and that will be less than 2 raised to the power log n plus 1, and that's the rough estimate of 4n. Okay, so that's why you can just allocate 4n space, and then say, hey, this is the space complexity for segment tree. But it's still linear, right? It's not quadratic. The growth is still linear. Segment tree only requires linear number of vertices. Linear does not just mean n, though. It's 4 times n. Okay. Height of the segment tree is log n. That's predictable because it's still a binary tree. So how do we construct the segment tree? So there are two ways, bottom up or top down. So we'll look at the bottom up first, because the one observation that I immediately made was that the leaf items of the segment tree are just individual array element themselves, right? So sum from 0 to 0 would just be the element 0, that is 1. Sum from 1 to 1 would just be the element at index 1, which is 3. Similarly, sum from 2 to 2, sum from 3 to 3, sum from 4 to 4. So there, so 1, 3, minus 2, 8, 7 just match the original array here, 1, 3, minus 2, 8, and minus 7. So this means that the leaves of the segment tree will just be the original array. And we can already tell if the leaves are O(n), we definitely need more space than order of n. Okay, what else? So we've gone through the height, we've gone through the space complexity. Okay, we were trying to figure out how do we construct the segment tree, and the idea was to go from bottom to top. So the value gets stored. Yeah. So and of course this makes it slightly easy intuitively to understand, because once you have the original elements and you're always going to be starting from the original element, all you need to do is effectively just merge these together using merge operation to get the parent, right? So if you see, okay, I want the sum from index 0 to index 1, and I already have the sum from index 0 to 0 and then from index 1 to 1. Then I can just sum them up. So I can just say sum equals 1 plus sum equals 3 is sum equals 4. So if you merge these two together, you get its parent. And then if you merge these two together, you get its parent. And then if you merge these two together, you get its parent. And then you merge these two siblings together and you get its parent. And then that's the root node. So that's the bottom up way of creating a segment tree, right? You start with the leaves and then you start merging them together to get partial sums that apply to the parent, and then you recursively do that until you get to the root, which has the broader sum. This might itself be not be enough. This might not be enough, because yeah, so exactly the value that gets stored at each node of the segment would store, a node would store the sum of elements in this range. The merge operation would merge two siblings, etc. And then you get you start with the leaf and then you go to the root. Yeah, we start. Yeah, okay. So this is exactly what I just said, but slightly more concise, I suppose. We start at the bottom, the leaf vertices, assign them their respective values. On the basis of these values, we compute the values of the previous levels using the merge function, etc., etc. And then we get to the root element, right? So that's kind of the idea. So this is very convenient in terms of understanding how the segment tree works, but probably this is not the way we are going to do it. It's probably easier to break things down if you already have an array and then kind of have sub partial sums, etc. I don't know. But let's see. Okay. What is a top-down way to compute the segment tree? Yeah, the top-down way is actually just going the opposite, right? So you compute the sum, but I'm just wondering how this will work. If you will you still end up computing partial sums over every operation, because you don't have a merge operation which can conveniently go from 2 plus 1 to 3, right? How do you break 3 into 2 and 1? That's what I want to get. Is that even possible? Probably not. Or do you just do a two pass? You first break down the array to compute the tree, and then you sum it up going from bottom to top? How do you do that? The time complexity, okay, for the bottom solution, the time complexity of construction is order n, assuming that the merge operation is constant time. Yeah, that's kind of an important consideration. Yeah. So in the sum case, what it's trying to do is, I guess that's it. It's just trying to do bottom up construction. That's it. Yeah, it is convenient to describe this operation recursively in the other direction. That is from the root vertex to the leaf vertex. The construction procedure, if called on the non-leaf vertex, does the following. Recursively constructs the value of two children vertices, merge the computed values of these children. Okay, so first you have to compute the children like recursively get the child, and then you do the merge on the children. Okay. I guess it'll become more clear when we get to the code. But now let's say you have the segment tree, right? So let's say you have the tree. What do you do then? Well, if you have the tree, how do operating on the segment tree? This is what I want to know. Let's say you have a segment tree going from, okay, you just have a tree, right? We created our segment tree. So now you need to compute sum over some array L to R. How do you do that? So the first thing you do, you get a mid, and the mid would be L plus R by 2. Divide the array into two subarrays. Well, not divide the array, but yeah, divide the range. You want to divide your range, right? To compute into two sub segments. So one would be like going from L to mid minus 1. No, just L to mid, and the other would be from mid plus 1 to R. Right? So that's what we're doing. Yeah, here you go. Yeah, so mid is, yeah, so TM is TL plus TR by 2. This is exactly what we did. We have like a mid, M is equal to L plus R by 2, and then we just say, we got this range, right? So we got like L to M. Yeah, L to M. This is one segment, and then you have like a segment M plus 1 to R. And now you can have three cases. Now you can three cases. And okay, so first figure out, let's say you are currently at some random vertex inside the segment tree. So you're pointing at some element. So you start at the root, but let's say you're not at the root, you're at some element in the middle. You could also be at the root, you could be at the leaf, doesn't matter. It's just solution is probably generic. So, but we're still going to think about that we are somewhere in the middle. So now you can have three cases. Either that the range at current vertex is directly equal to input range L comma R. We are done. We can just you already constructed the tree has a sum at that particular node, so we are done. Range is completely in the left or right child of current vertex. Let's say it's in the left child. So let's say the range is, let's say the input range is, currently at some random vertex, and then let's give this vertex a name. Let's say U comma V, right? So what we are saying is that if U comma V is completely inside the left child of, actually no, what we're saying is L comma R is completely inside the left child of U comma V, right? That's what we're saying. Go to LR by traversing the left child, you are done. Because you started at some range, probably easy to get explained visually. So you started at 3 4, and the question asks you to get the sum from 3 to 3. So all you need to do is just go to 3 3, go here, and then you're done. The sum is 8, you're done. And same thing applies for the right. Or the answer is the range is so go to left child, compute partial sum, go to right child, compute partial sum, merge the results, you are done. So this can happen if you need different partial sums than you have right now. In this case, we simply go to the child vertex, cover the segment. Last case, the query segment intersects with both children, right? So the query intersects with both children. That's the kind of the idea. So let's say in this case, it would have been 2 comma 3. So let's say you want to get the sum from starting at index 2 and going to index 3. So you cannot just go only to the left child, because the left child has no knowledge about index 3. You cannot just go to the right index, because the right child, because the right subtree has absolutely no information about index 2. So you need to consider both. So you need to first go to the left child, and then from here you'll probably go to the right child, because that's the only child which has information about segment 2, and that's contributing the sum -2, right? So you get this -2 here. I don't know how you bubble that up here. We'll probably figure that out. And then you need to also do the same with index 3, and then that's contributing the sum 8. So -2 plus 8 would be 6. So what's the thing, right? So if we go to, -2 plus 8. So index 0, 1, 2, 3. So from 2 to 3, that's the sum. So you need to partially, you need to sum up the partial kind of results. So that's kind of the third, more complicated case. So processing a sum query is a function that recursively calls itself once with either the left or the right child, or twice, once for the left and once for the right, by splitting the query into two subqueries. And the recursion ends whatever the boundaries of the current query segment coincides with the boundaries of the segment. Yeah, whenever the boundaries coincide, that's when the recursion ends. In that case, the answer will be the pre-computed value of the sum of these segments, which is stored in the tree. In other words, the calculation of the query is a traversal of the tree. This makes sense, which spreads throughout all necessary branches of the tree and uses the pre-computed sum values of the segments in the trees. Otherwise, we will start the traversal from the root values of the segment trees. So now we have an example here. The procedure is illustrated in the following image. Array is the same. Here we want to compute the sum starting from index 2. So this is index I equals to 2 to I equals 4. And yeah, I was using 2 3, but hey, let's just use 2 4. The colored vertices will be visited, and we will use the pre-computed values of the green vertices. This gives us, okay, so let's just go. We start from here. We visit this because we need to visit both children. So we go from here to here. So we want to go from 2 to 4. So probably the information from 2 will be used from here, and then we go to 2. We get the sum from array 2 dash 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 2 dot 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 2. So we get this green value here. And then because the rest of the items go from, okay, YouTube is asking me to verify if I'm really you next. Why does it need to verify if it's really me? Okay. Get a verification code from the authenticator app. Where the hell is my authenticator app? Okay. I don't know, but let's say. Okay, it's me. I'm back. Right. So we wanted to compute the sums from 2 to 4, right? And for 2 to 4, we need to go get the sum at index 2. That's going to be in the left subchild, the left subtree, and then get the remaining sum, which is starting at index 3 and going up to index 4 from the right subtree. And hey, this completely matches there. So we get minus 2 plus 1, and that's going to be minus 1. And that's the answer. So this is pretty convenient visually. I'm just going to be super curious about how we are going to play this out in the actual program itself. Is it going to be one of those elegant recursive solutions? Because how do we bubble up? I guess bubbling up the child values are also isn't also not that big a deal. So what's the complexity? The complexity is probably just going to be log n, because all you're doing is just traversing the tree and then fetching values, right? To show the complexity, we look at each level of the tree. It turns out that for each level, we only visit not more than 4 vertices. For each level, we only visit up to 4 up to 4 vertices, right? So okay, so we're at this level, we visit this. Okay, I don't know. I don't understand this sentence. Since the height of the tree is log n, we receive the desired running time. We can show this proposition at most 4 vertices each level is true by induction. At first level, we only visit one vertex, the root vertex. So here we visit less than 4 vertices. Now let's look at an arbitrary level. By induction hypothesis, we visit at most 4 vertices. If we only visit at most 2 vertices, the next level has at most 4 vertices. Okay, this is trivial. Oh, okay, is that what you're saying? Like if you're at this level, we can only have like 4. If this one has 2, then the next one has 4. If this one has 4, the next one has, I don't know, 1, 2, 3, 4. 8, etc. We visit at most 4 vertices. If we visit at most 2 vertices, the next has at most 4. This is trivial because each vertex can only cause at most 2 recursive calls. So let's assume that we visit 3 or 4 vertices in the current level. Okay. From those vertices, we will analyze the vertices in the middle more carefully. Since the sum query asks for the sum of a continuous subarray, we know that segments corresponding to the visited vertices in the middle will be completely covered by the segment of the sum query. Therefore, these vertices will not make any recursive calls. Okay, I am losing track. I think what it's trying to do is it's trying to figure out the amortized cost by saying, hey, you're more often than not, you're only going to be visiting these vertices and then blah, blah, blah. And so it's kind of estimating. So only the most leftmost and most left and the most right vertices will have the potential to make recursive calls, and those will only create at most 4 recursive calls. So also the next level will satisfy the assertion. So we can say that one branch approaches the left boundary of the query and the second branch approaches the right one. Therefore, we visit at most 4 log n vertices in total, and that is equal to the running time of log n. Okay. In conclusion, the query works by dividing the input segment into several subsegments for which all the sums are already pre-computed and stored in the tree. If we stop partitioning wherever the query segment coincides with the vertex segments, then we only need log n such segments. Yeah, update queries will be more interesting, right? This is kind of getting the sum. But how do you update? I guess that should not be that difficult. Now we want to modify a specific element in the index. Let's say we want to some assignment I equals x, and we have to rebuild the segment tree such that it corresponds to the new modified array. This query is easier than the sum query. Oh, okay. So each level of the segment tree forms a partition of the array. Therefore, an element AI only contributes to one segment from each level. Thus, only ON vertices need to be updated. Hey, that's pretty cool. Yeah. So it's going to be at some element like 2 contributes here, 2 contributes here, 2 contributes here, and these are the only 3 items that need modification. There you go. It is easy to see that the update request can be implemented using a recursive function. Easy to see. Okay, so we did the update, right? So we modified the array, the second index of the array, to give it number 3. So the green vertices are the vertices that we visit and update, right? So this used to be -2, I think. Yeah, this used to be -2. So now instead of -2, this became 3. So we pushed, and then we kind of pushed that up, and then we modified this sum, and then we pushed that up, and then we modified this sum, and that's it. And so we need to do log n operations. The main consideration is how to store the segment tree. Of course, we can define a vertex struct and create objects that store boundaries of the segments, its sum, and additionally also pointers to its child vertices. So basically what it's saying is we can just make, just like a linked list or a graph, we can just create a tree class. However, this requires storing a lot of redundant information in the form of pointers. We will use a simple trick to make this a lot more efficient by using an implicit data structure, only storing the sums in an array. The sum of the root vertex at index is at index 1, the sum of its two children at index 2 and 3, the sum of the children of those at index 4 to 7, etc. So kind of like a binary heap, okay? This simplifies the implementation a lot. We don't need to store the structure of the tree in memory, it is defined implicitly. We only need one array which contains the sum of all segments. As noted before, we need to store at most 4n vertices, so we know that. Let me just open a C++ file. I'm not a C++ expert, but especially not in the context of competitive programming, but probably it would be nice if we could just do that, right? So, right. So what you're saying is, so this is what we typically do, right? Pound include iostream. So what it's saying is int n t4 into max n. So let's say that's kind of your array size. So max n, I don't know, let's say 10. So we store the segment tree simply as an array with the size 4 times the input size n, right? So the input size is n. I don't know. Let me just do this. Get from input. But what do we have here? So the procedure to construct a segment tree from a given array A. Okay, let's just do this, right? So I don't know. What was the array again? 1, 3, -2, 8, -7. Okay, so we have this. What do we do now? We need to build the segment tree. How do we build it? So let's just call a separate function called void build. Okay. So it's getting the procedure for constructing the segment tree. It's a recursive function, right? So this is a recursive function. What are the elements? B is the current vertex. TL and BR are boundaries of the current segment. Okay. So initially it'll be like at root, you have like A, B equals 1, equals 0, TR equals n minus 1. Why is B1 at root? Why is the current vertex 1? I don't understand this. But hey, let's say if TL equals TR, T V equals ATL. This makes sense. Tm is equal to T plus Tr divided by 2. And then you recursively call using A. The current vertex will be twice TL and Tm. A twice plus 1 Tm plus 1 Tr. And then Tv is equals to T times 2 plus T 3 times 2 plus 1. Okay, I think this is mostly for the array representation, right? So if you're the current representation and you want to go to the left child, you're just going to be like at index, it'll go twice the index. And the right child will be at 2 plus 1, right? That's why you're probably trying to do this. One indexing, convenient. Yeah. Okay. An array representation of right, and this is kind of the idea. What does it say? Let me just write it down. It says with one indexing, conveniently the left child of a vertex at I is equal to index 2, 2 into I, right child of a vertex at index I, index 2 times I plus 1, right? Okay. You need to remember a lot of these tricks, right? So now that you can kind of see that we are current vertex V, and we are indexing, so this is the current index, right? So yeah, okay, I get it. Yeah, equivalently, the parent of a vertex at index I is stored at I by 2. Parent of vertex I is equal to I 2 integer division. So this is kind of really useful to remember for segment trees, that make sure your array-based indexes are one base, because then you can kind of use these tricks. So what we are saying is we start with like some boundary condition. And true 0 to n minus 1, like they're going to be reducing, but they're not initially there. So okay, we get the middle value, and then we build it, and we recursively on the left child, and then recursively on the right child. So this is going to call the same thing with the left child and the right child, and then within that left child, what it's going to do is yeah. Okay, so let me just do this. Int left child is equal to v to 2. Int right child is equal to v times 2 plus 1, right? So then I could just say that. I could just say a left child, right child, and then I know what I'm doing here. I am doing left child, right child. So you're building up this is kind of a merge operation, right? So this is the merge operation. Okay. Further, the function for answering sum queries is also a recursive function. So this is just for building the segment tree, but what about the function to answer sum? So this one has some extra parameters. It receives as parameter the information about the current vertex / segment. So that will be like V and TLTR, and also the information about the boundaries of the queries, L and R. Yeah, because it needs to know which is the range. In order to simplify the code, this function always does 2 recursive calls, even if only one is necessary. In that case, the superfluous recursive calls will have L greater than R, and this can be easily caught. Okay, so let's just do this. If L is greater than R, return 0. If L equals TL and R equals TR, return V. So this is the kind of the first case, right? Which is your incoming range completely covers the index, the range where we are currently at. Otherwise, TL plus TR divided by 2, and then return some. Yeah, it's the same thing, right? So let me just copy over these things in left child and right child. So otherwise we are going to do like sum of like left child going from TL to TM, and the sum is going to be L minimum of R to TM. I don't understand this. Plus sum right child TM plus 1 TR max of L TM plus 1 R. I don't understand this at all. Yeah, this min-max business is kind of tricky. Okay, I think this is good enough for now. I'm just going to go and watch some videos and try to understand it better. We can do that on the stream. I don't mind it. Are there any good videos explaining segment trees? Yeah, what about this guy, right? Okay. Segment trees. Does he have a second video in which he actually explains the implementation? Yeah, I don't know. Getting a bit tired. I'm gonna end this stream and then figure out what's a good way to approach, because I like clear and intuitive implementations. I'm not going to copy any and not understand what's going on. Like I don't know what's going on here with like the minimum, and I don't have the brain energy right now. So I'm just going to pause the video right here, and I guess we'll end it. Bye bye.